Let's look at the limit as x approaches 1 of the absolute value, x minus 1, divided by x minus 1. And so we'll let x, somebody will use different colors so it stands out, right? What are we assuming? That x is infinitely close to 1, but x isn't equal to 1. So this tells us that the standard part of x is equal to 1. Okay, so those are our assumptions. And yeah, notice I've used the variable x instead of h. I hope that's not confusing, but these are just kind of dummy variables. We're going to let x be infinitely close to 1, but not equal to 1. And that means that the standard part is equal to 1. Okay, so what is this equal to? Well, this will be equal to the standard part of the absolute value of x minus 1, all divided by x minus 1. And since the standard part of x is 1, the top would be 0, or the absolute value of 0, and the bottom would be 0. So we can't use our quotient rule. We need to get rid of this absolute value somehow. However, how do we do that? Well, let's remind ourselves. What is the absolute value? So I'm going to kind of block this off. So this is our work reminding ourselves about absolute value. So the absolute value of x minus 1 is equal to, well, it depends. It's going to be equal to x minus 1 if x minus 1 is positive, right? If it's bigger than or equal to 0. And it's going to be negative x minus 1 if x minus 1 is negative. Now, this is a little bit awkward. Let's rewrite this in this way because of the inequalities. We can bring the 1 over. So this will be x minus 1 if, so adding 1 to both sides. So if x is bigger than or equal to 0, not 0, sorry, but 1. And it's going to be negative x minus 1 if x is less than 0. I keep saying 0, but x is less than 1. Now, let's remind ourselves, x cannot be equal to 1. So this equal sign that we wrote here is actually not allowed. So we can't even be equal to 1. So actually, let me erase that because we can't allow equality. Okay, so now we've got the absolute value. X minus 1 is equal to this if x is bigger than 1, and it's negative x minus 1 if x is less than 1. Which means this standard part, to get a handle on it, we need to break it into 2 cases. So case 1 is when x is bigger than 1 and x is infinitely close to 1. Then the standard part of absolute value x minus 1 all over x minus 1 is equal to, well, what's our rule? If x is positive, if x is bigger than 1, then absolute value can be replaced with just x minus 1. So this equals the standard part of x minus 1 over x minus 1. And this is equal to the standard part of 1, because x minus 1 divided by x minus 1 is 1, and so that's just equal to 1. However, case 2, in which x is less than 1, but still infinitely close to 1, then in this case, the standard part of the absolute value x minus 1 divided by x minus 1. Well, now if x is less than 1, we have to use the second rule here, that we've got to replace absolute value of x minus 1 with the negative. So this is equal to the standard part of negative x minus 1 divided by x minus 1. The x minus 1 still cancel, but now I'm looking at the standard part of negative 1, which is negative 1. And notice what just happened. If in case 1, x is positive, or x is bigger than 1, then the standard part is 1. But over here, if x is negative, the standard part is negative 1. So depending on which values, or which side of 1 you are, you get two different values for the standard part, which means this does not exist. There is no standard part. It's bouncing back and forth. It's either negative 1 or positive 1. And so this limit itself does not exist. And it's quite possible, happens often, that limits don't exist. And we can look at the picture to get a sense of why. So I could graph, let's do a graph here of x minus 1. So here's the y-axis, here's the x-axis, and say here is where the transition happens. So here's where 1 is, and the graph looks like this. This ratio is actually always 1, and so this is what the graph looks like. This is at the point 1, and it's negative 1 otherwise. So this is our graph, and at this point, at positive 1, kind of put a dashed line there, we have, if we're on this side, we're very close to positive 1, but if we're on the other side, we're very close to negative 1. And so the limit, you kind of think of the limit as values of x are getting close to 1 but bigger than 1, the function is getting close to 1 itself. But if the x input is approaching 1 on this side, then the output is here at negative 1. And this is a motivation for defining what are called one-sided limits, left-hand limit and right-hand limit. So let me make some room, and we will put that definition up here on the board. So the right-hand limit of f of x is defined this way. L is the right-hand limit of f of x as x approaches c from the right if whenever h is infinitely close to c but strictly greater than c, f of h is infinitely close to L. So again, it's kind of a word fest here, but let's take a look at the symbols that are going here, and notice it's this positive sign. So all of a sudden this C, that's what we're getting close to, has a positive and as kind of like an exponent. And so this positive C is we're saying that H will be infinitely close to C but strictly bigger than C, then this limit would be the standard part of f of c, provided it exists. And similarly, we have a left-hand limit. And the verbiage is exactly the same, except for now we're going to be strictly less than c. So again, in symbols, what we have here is a minus sign to denote that we're less than c. So again, what are we doing? We're going to say h is infinitely close to c, but h is strictly less than c, and then this limit would be the standard part of f of c. And so in the previous example, we saw that the left-hand limit, so the limit as x approaches 1 from the left of the absolute value of x minus 1 divided by x minus 1 is equal to negative 1, but the limit as x approaches 1 from the right of the absolute value of x minus 1 all over x minus 1 is equal to positive 1. And we can say that, as we saw in that problem, this limit doesn't exist, and in fact this gives rise to this theorem, which states that a limit has a value. In other words, it exists if and only if both of the one-sided limits exist and are equal to the same number. So this can be a way to really check to see if a limit doesn't exist, is by taking left-handed and right-handed limits.